Okay. Okay, so we're ready to go. And I thought today I'll do the similar to what we did last time, but I would do it with the we'll do it as a strategy pattern, okay? So let's try this one more time, okay? And this time we'll pick a real this is an example from the book, okay? So and then we'll move on to other things. So just to review for a second, where's that document? Um, okay. Does anybody remember let's actually open up IntelliJ. So today we're going to let's do the duck pattern. We'll do the strategy pattern, okay? So, okay, the first design pattern and strategy pattern spring 2026. Okay. Okay. So let's start out with we're going to be using the famous duck example. Okay. So let's say, for example, we have um, a duck which is a interface. Okay. Okay. And actually, let's make this a class. I'm sorry. Actually, let's make this interface. And then, okay. So now in here, is duck a concrete or abstract class? Okay, again, duck is a interface, right? Because let's say it has let's give it some methods. So remember, it's an interface, so it doesn't have any code. It just has a description of what it could do, right? Doesn't really actually do anything. It just describes what a duck could do. So let's have a quack behavior or method, and we'll have right, like a duck goes quack, 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 and we'll give it a, um, a quack and a fly. Okay, so the duck could either quack or fly, right? It makes noise or it could fly, right? So is this a concrete class or a abstract class? And how do you know? So if you remember from last week, what do we say? If it's very easy to tell because if you could go duck dot d oops under small d equals to new duck, uh, if you can't if it won't let you just do this, what does that tell you? It tells you that this is not a what's called a concrete class, meaning that it's not a real class. Because why is it not a real class? There's no code, right? There's nothing to create because all it does is describe what it could do, right? But it doesn't actually do anything, right? Okay, so let's say we have let's do another class. So so this is called a abstract class, okay? Okay, so that's number one, abstract. Okay, now let's try a real concrete duck. Okay, so let's call something called a regular duck and regular duck. And this duck could is a regular, and this one was going to have the same methods, except it's going to be not an interface, it's actually going to do it. So it's a regular duck, and it has these two methods called quack and Um, so a quack is going to um, uh, just regular quack, and over here we're going to have wrong thing. It goes over here. We're going to do a regular fly. Okay, regular. I don't know. What's a duck do? Duck. I don't know. Swims. I don't know. Regular, whatever, fly. Okay. Regular flying and regular quacking. Okay. So now we go back over here and we can't create a duck because that is a abstract class, right? So, but we could do is we could do regular duck equals to new regular duck because regular duck is has code inside of it, and we could call quack and fly, right? So far, so good, right? So now we can say regular duck dot fly, and then regular duck dot quack. Okay, now here's where things get interesting. So far we've seen that you could have a abstract class which you can't create and a concrete class. This is called a concrete class. So let me put a comment here. This is called this um, is called a concrete class because it can be um, created with the new operator, right? Okay, so now we got these two. Okay, so far so good, right? So we have a concrete and we have a abstract class. Now, let's say, for example, we want a duck, which is like a regular duck, except that it doesn't know how to fly. Let's say it's a baby duck class, okay, or whatever, the type of duck that doesn't fly. So we're going to create, so we say, let's do that by through inheritance, right? So, so we're going to have a new type of duck, and this new type of duck is going to be a, um, what do we say it was going to be? It was going to um, non-flying duck. Okay. Okay. But the quacking part we like, right? Regular duck has quacking, which we want to do, but we don't want to do flying. So we'll inherit from the regular duck, right? So now we got the quacking, right? But we're going to, but the quacking, I'm sorry, the flying part, we're going to um, get rid of, right? Because we don't fly, okay? Okay, so we're inheriting the quacking. Does that make sense? So if we go back over here, so we have a, now we have a non-flying duck. I'll just say NFT equals to new NFT and get rid of this guy over here. And um, and now NFT is going to still do the quacking the same, but the flying is going to um, be different. So let me just go like this. Hold on. Come on. Okay, NFT fly and NFT quack. Okay. So if we run this now, we'll see that. So we say, the first duck does regular flying, regular quacking. The second duck does quacking, but not flying, right? Why? Because we took that away where the child of regular duck said, I don't want to do everything that you do. I want to do my flying differently, right? Okay. Now, then what happens is, let's say you want to do something the other way around. You want to have a non-quacking duck, okay? So we have a non-quacking duck, and then we're going to extend, um, um, we want to extend duck, I'm sorry, regular duck, and we're going to, uh, we have to do for the quack, it's hard to keep track already. For the quack, we have to say, I don't quack. Okay. Now, let's say we want to have a duck which, um, with, let's say, oh, now let's say we want to have a duck which doesn't do either quacking or flying, right? So what do we do now? So now, um, I guess non-flying, uh, oh, let's say, oh, actually, let's say um, it does, actually, this is called uh, a red, let me think for a second. Uh, yeah, I mean, it's kind of, okay, it's kind of silly, but let's do this. A red, non, a non-flying, non-quacking duck. Okay, so we have one which is going to inherit. Now, theoretically, we could, we should really, we could actually inherit, since we're non-flying, non-quacking, we could inherit from either the non-flying or the non-quacking, right? But it's already getting kind of complicated, right? Really, we should really be able to do is, um, okay, so let's inherit from one of them, non-quacking, and then we have to remember to override flying. So, fly. Okay, so basically, after a while that we have let's say we have another duck which is going to be a, um, it's going to be, so we have all the, wait a second, we have flying duck, but, okay, okay, let me think for 1 second. Now, let's say we have we have a regular duck, we have non-quacking, flying, quacking. Uh, oh, okay. Let's say, for example, we want to have a duck which is, what is it? Regular duck. Okay, which does regular flying, but doesn't do regular quacking. So, no, I'm sorry. it does, oh, actually, let me put one more thing in regular duck. So let's say, for example, in regular duck, let's give one more method, and we'll call it void. No, let me put over here. So I'm trying to not to make too many classes. Um, let's say this is, um, let's put a, um, um, okay, we'll make one more method called void display, and then I look like a regular duck, and then over here, let's say we have, so then let's say we have over here, we have, you want to have a non, a red duck, um, you know what, well, okay, well, let's just leave it like this because it's going to get too complicated. So the idea is that if you see all these different inheritance, every time you change a behavior, you have to worry about, in other words, if I look over here, okay, just by looking over here, a non-quacking duck, I don't really understand, like, where was it? It was non-flying. Like over here, it's not clear. Where's, is this here? Never used. Okay, thank you very much. Get rid of it. How do I get rid of it? Uh, uh, Did I get rid of it? Okay. So, the point is like this, is that if I look at this code, it's very non-intuitive that I'm getting a non-flying duck, but, I am getting a quack, right? So in other words, it's basically, that, um, it's basically it becomes very complicated. In other words, if I want to know does this duck quack, right? So I have to look at its parent, and then if I look at its parent, I still don't know if it quacks until I look at its grandparent, right? So it gets after a while, it becomes very, very difficult to follow the logic because I'm just inheriting certain logic, overriding other logic, and after a while, it becomes a big mess, right? Okay, does that make sense? Right, so you see it right because you can see over here this right away. Um, the the book that gets example goes through more, adds more classes, but I don't want to, get stuck in all that. But the point is that even from these, we have like a third, like a child class and a grandchild, right? So we have this one over here. It's not clear by looking at it what it does, right? All we know is that it inherits from non-flying duck, but we don't know what a non-flying duck does, right? And then when we even look at a non-flying duck, it's not clear what it does, right? It's only clear once we go over here that that there's a quack over here and there's a display over here, and then we have to go back and see what what the children are doing to these methods, right? So it gets very complicated, right, to use. You could imagine, right? And then let's say you like a little bit of one, but you don't like all of it. So this whole inheritance thing gets very, very complicated, okay? Because we're getting a lot of different things, right? But we really over here we really just want the non-flying part, right? But instead we're getting everything, right? We're getting quacking and non-flying, and or right, and over here I'm sorry, over here we don't want to get the flying, we only want to get the quacking, and over here we really don't want to, we just want to get the display part, right? and we don't really want to get anything else, right? But we're getting it. So, so the idea of so one of the ideas of inheritance is that it's making everything very complicated, right? Becomes very complicated to follow all the classes and to know which class to use and which class to inherit from because it's so, each one is turning things on, the other one turns things off, and then eventually, it gets it becomes a big mess. Okay? So inheritance, so basically the problem with this is it's just too complicated. So um there's also actually two problems. So I'll just write it over here. So actually I'll write in this document. Um right over here. So okay, so I'll just put over here. So number one is there are two, well, there's one big problem, one major problem. Actually, the we'll start with the fifth object-oriented principle. I call it number five. That's my own numbering system. So the first object-oriented principle is going to be that we prefer composition to inheritance. So that means that whenever possible, we avoid inheritance for two reasons. The most important reason is because it gives inheritance gives us too much um, it gives us um, a lot of code which we um, have to be aware of and understand. And this makes the child classes very difficult to code, right? Because basically everything because getting all this code from the parent, and when you're looking at the children, you don't know what's going on, what it's getting from the parent, what's not getting. Uh, that's number one. Number two is what's called the fragile base class, which I think we mentioned this also, which is that the parent that changing the changing the parent class can break the the children, right? Without us noticing, right? So by accident, it's very easy to break all the children that inherit because they're all depending on the parent. Okay. And number three is that um, the when you do it, at least in Java, inheritance can only be from one from you can only inherit from one parent, right? So, for example, over here, remember we had the no fly, no quacking. We weren't able to inherit from non-quacking duck also, right? We had to choose which one of them. So we pick one of them at random, right? We could have inherited from non-quacking, right? But you can only inherit from one. So it's kind of limited. So it forced us to arbitrarily inherit from only one of them, and then we had to override the other behavior, right? It would have been a lot better if we could inherit it from both. So in Java, you can't, inheritance can only be from one parent. Okay, so with composition, so this is object-oriented principle number 5. Okay, we'll go through what the other first four are. Okay, but right now we're just dealing with that. Okay, so now let's look at another way to do. Um, I'm going to skip the second way we did last time. Okay, and we'll go straight to the third way. Okay, the third way is what's known as the strategy pattern. Okay. So what the strategy pattern says is it says that we should separate um, behavior that changes into its own object that can be passed in by itself. Okay, so basically, what is the strategy pattern saying? Saying like, if let's look over here at this duck again. At this duck, we have certain things that, if you look at a regular duck, you notice that this doesn't change, right? The display doesn't, um, the children aren't changing this, right? But the fly and the quack, they're changing, right? And because they keep on changing by the children, the children always have to worry about it and override it, right? But is there another way to do it? Well, and then if there's a better way to do it, then we maybe don't have to create all these different children, right? So what would be that way? Well, the strategy pattern says take those behavior that changes. What changes? What is changing? The quack and the flying, right? And put those into separate objects. Okay. So what we're going to do is we're going to create a new object and um, and what we're going to do is we're going to have object called quack, and we're going to have which is going to have a method called quack. Small quack, and quack, and then we have another one called fly, which is going to have another method in it called fly. Notice that everything is lowercase. The methods are lowercase because in Java, methods are lowercase, right? So we're going to, over here, we're going to, um, okay, so now we're doing now the strategy pattern. And what we're going to do now is we're going to take our, let's make a new type of duck called um, I don't know, I ran out of names for ducks. Let's call it a duck. Um, what? What? A, say again?
Like ABIN.
ABIM?
Like a set of flying birds like avian.
What? I think, uh, ABM? Okay. I don't know. I'll call it, duck, duck, let's call it, the strategy duck. Okay. Okay. The strategy duck. Okay, so the strategy duck is going to be a little bit different than the previous duck. So what's going to have is it's going to have the same methods as the regular duck, but watch what we're going to do different. What we're going to do different is this is going to stay the display, but the when we create this, what we're going to do is we're going to have a quack uh, pointer, like a reference to quack and to fly. And then we're going to we're going to pass we're going to pass those in when we create this strategy. We're going to in the constructor, we're going to pass in these objects. So we're going to generate, and we're going to um, pass in these two guys. And so these guys are going to be set when we create the strategy duck. And then when we want to fly, we're going to call quack, dot quack, and then fly dot fly. Okay, so what do we do differently now? So now we have composition, which means that the quack is not inherited, right? But rather it's passed in when we create the strategy duck, right? So the type of quack it's going to do is passed in. And now, if we want to change what type of quack it's going to do, or what type of fly it's going to do, all we have to do is pass in a different type of quacking behavior. Okay? Does that make sense? So we're not inheriting it, but we're passing it in. Okay? Now we have to make one little change, which is that we only have, because right now I'm using uh, a specific type of quacking, right? This is a quack is this concrete or abstract? Well, let's see. We look at it, it's a regular class, right? So now our strategy duck could only take one specific type of quacking and one specific type of flying, right? Because they're concrete. Um, and so we'd rather pass in something like more generic. Now remember, what's the great way to, if you remember from the first from Tuesday, what is a great way to group things together? Like remember, like cooks, like if we have a bunch of cooks, how can we group? What's the one way to group them together? Well, do they know how to, let's say, bake breakfast? Not bake, cook breakfast, right? So if we use an interface by what they do, then we don't have to restrict ourselves to any concrete class. So what we're going to do now is we create two interfaces. One is going to be um, a flying interface. And this, I'm sorry, and this is going to be an interface. And all this is going to do is have a fly method. And then we're going to do the same thing for the quack. We're going to have a quacking interface, which all it's going to do is quack. Okay? Wait, over here. Okay, so now look at what's going to happen. So now we could go to the we could pass in, we go back to our strategy duck, and instead of having a quack, this to be a concrete class, which is very specific to only one type, we could have this quacking. Okay, and this could be flying. And then over here, we can make this also be a type of quacking. And this could be a type of flying. So instead of passing in a specific type of class, all we have to do is pass in a class that supports flying and quacking. Get it? So now instead of being stuck to just one type of class called quack and fly, we could actually pass in anything that has a quack method and anything that has a fly method. So we just improved our code to be more generic. Okay? So far we've done two things. Number one, we got rid of inheritance. Number two, and then, so how are we getting our flying and quacking? We're passing it in, right? We're putting them into their own objects and pass them in. Number two, we're passing them in not as a concrete object, but as something which is the type it's using is something that all it needs to do is have the quack or the fly method, meaning you don't need to. That's the only thing we require. It doesn't have to be a specific class, but any class that has this that supports the quack ability, who has the quack ability. Okay, does that make sense? Right? So we did two. You see the two changes we just made. One was we got rid of inheritance. We pass in the behavior, right? Number two is we said you don't need a specific concrete behavior or object. We could take anything that has a quack or has a fly within it, a fly or a quack method within it, that we're going to support them. Okay? And therefore, we're going to go back to our quack over here, and we're going to define them as supporting the quacking and flying behavior. So we're going to say that this implements the quacking behavior, and we're going to say the fly implements the flying behavior, meaning that it could do a lot of things, but one of the things we wanted to do is implement this flying behavior, meaning it has a fly method, which it does, right? Okay, now we could go back. So how would we use it? So let's try it. Okay, let's try it this way. So let's start with our strategy duck, right? Which is going to be equals to new strategy duck. Now we're going to have to pass in to it. Let's give it a better name than strategy duck. Let's give it let's call it a regular duck. Okay. Or let's call it a normal duck. Normal duck. or standard duck, okay. Standard duck. And that's going to pass in, we're going to pass in the, what does it want? It wants, I think, the quack and then the regular flying, okay? And now we pass in that, and then we go over here, and we could say standard duck, standard duck dot fly, and standard duck dot quack. Okay, so what we did now is we're passing in the behavior that we want. Now, let's say, for example, we have a duck that doesn't fly. Okay, so we could go over here and we could create a new behavior called no flying. And then this could implement the flying behavior, and it will have a method of fly called what did I just do? Go back here. I clicked something. Oh, here we are. So it just gets so complicated with all these. When I use the large fonts, it gets very messy. So over here, it's going to say, I don't fly. And then we could have a no quack method called I don't quack. No quack, which has a method called which implements quacking. And it's going to, when we create the method, the quack method, it's going to say, I don't quack. And then if we go back, and since the no quack and the quack both implement quacking, right? Therefore, we could pass both of them, either of them, and the same thing with the fly and the no fly, both implement flying, we could pass them into here. So we could have we could have like, we could pick and choose. So we could have no, um, a do nothing duck, do nothing duck over here, and we'll pass in no quack and no fly. And then let's see what happens. Okay, so let's just comment this out for a second. Okay, let's see what happens. So now, so you notice we didn't change this code, this class, right? We didn't create any new classes, any new types of ducks, right? What do we add? We just added different ways of flying, right? But we're not like before, every time we changed the behavior, we created a new object, a new type of duck. Now we're saying there's only one type of duck. If you want to know what it does, well, you pass in the behavior that you want it to do. You see the difference? It's a totally different mindset, right? The first mindset was, well, we need a new type of object every time we do something different, right? This mindset is saying, well, you only have you have like this duck which will do the behavior that you give it. If you give it this behavior, that's what it will do, right? It's sort of like a module, you stick it in and that's what's going to do, but it's not part of the duck. It's something that you could change. You could swap in and out, right? It's not a um, it's not a integral part of the strategy duck, right? Strategy duck doesn't really care what what type of um, behavior you pass into it, as long as it has a quack and a fly, it's very happy to do it. It doesn't know what it's actually going to do when you tell it to quack or when you tell it to fly. It doesn't really care, right? It says whatever you give me, that's what I'll do. So for going back to main, we'll see that when we run this, you see that we wait a second. Oh, I'm sorry. I forgot to call the do nothing duck. A bad one. So the do nothing duck is now going to, so we have the regular duck, which is going to fly and quack, and then we have the do nothing duck, which doesn't do anything, right? Because we passed, that's what we told it, that's what we passed in. But the strategy duck itself doesn't change, okay? So this is really cool because here it's very clear what's going to happen. You don't have all this inheritance to follow. Well, what did I get from my parent? And do I like it? And if do I need to change it? Which parent do I inherit from? But rather, this mindset is, well, what do you want to do? Right? If you want to, do you want to fly or not? Well, if you do, then pass in a behavior for flying. If you want it to quack, pass in the behavior that quacks. If you want to, different type of quacking, well, just create a new behavior, right? So, for example, we could say we could create a duck like in the middle, right? Which we could do a fly but not quack, right? A fly only duck. And this is going to, we'll pass in the quack, but we won't pass in the fly, right? So that other way around. A fly only duck, so, I'm sorry, no quack. This would be fly, right? So we could pass in whatever mix of behaviors we want, right? Without having to create new objects, right? So that's what's so nice about this design pattern. Okay, we're getting away from creating new objects, inheriting, and then having more objects, and then getting lost in all the different inheritance. And instead, we're just passing in the behavior that we want. Okay, so we just created three different ducks, types of ducks, but we didn't have, well, we used the same duck, the same basic duck, and we just passed in the parts that changed. And it was clear when you look at the code, you could see what's going on, right? It's clear what we're doing, right? We don't have to sort of look at what its parent is and all that stuff. Okay. So if we run this now, you'll see that, we could just keep on mixing and matching, right? And we could create even more behaviors, right? Right, so over here I forgot to change this to fly only duck. Okay, so we do this and right, so here it flies and doesn't quack. Here it does both, right? So you could do all the different possibilities very easily and without creating new objects. Okay? Um, okay, so the strategy pattern actually has two different design principles. One design principle is number 5, which we explained, which was we rather not use inheritance. Do you see how this does composition? It does composition because we're passing in the behavior, so the behavior becomes part, or I'm sorry, not part, becomes inside. It's not, in other words, as opposed to being coming from the parent, the behavior is coming from inside of the object. So if you look at the strategy duck, you see that the over here, the quacking and flying behavior is inside of it. That's why it's called composition. So we prefer that the behavior be inside of it rather than coming from a parent. Okay? In this case, it means to actually, I would have said we prefer dependency injection. I guess that would sound really scary to you. Okay, and I would say it's really saying we prefer to pass in the behavior rather than inherit the behavior, right? It's easier to understand when you're passing it in, right, than when you're getting it from a parent that's in another object and you have to go searching to see what's going to happen. Okay? So that's what this means. Prefer composite inheritance means we avoid inheritance and instead pass in the desired behavior. Okay? And object-oriented number 6 is also based on the strategy pattern, is going to, actually, this should be over here. So strategy pattern is going to do 5 and 6. You asked what is 1 and 2, 1, 2, and 3, and 4. Does anybody know what 1, 2, and 3, and 4 are? You probably learned them already. That's why I started at 5. Okay, well, don't worry, we'll cover them. So, what?
The inheritance, the interface stuff.
Well, the first 4 object-oriented principles are like the basics. Like if you Google, you'll see these, like inheritance, polymorphism. You heard that, right? Inheritance, polymorphism, um, encapsulation. Which one? The abstraction, right? Those are the 4 main ones. Those are the 4 big ones that everyone knows. Right now, we're doing things that are a little bit. These are more not as well known. Okay. And then number 6 is going to be object-oriented principle number 6 is going to be that we it's going to be that we want to be open for extension, closed for modification. Okay, what that means is that, well, which means that over here, look what happens. Every time in main, where's main? We want to add a new type of flying or quacking. What do? We just create a new object, right? So what are we doing? We're adding code, but we're not changing existing code, right? We're not modifying, right, any other classes, right? We just keep on adding new behaviors as we go, right? So why is that so good, right? We're adding, but we're not changing existing code. Why is that good? Well, if you keep adding code, right, what happens and you're not modifying if you're creating new classes, right? No, it's where the most bugs come from. They come from when code is changed, right? But if we're not changing code, we're just adding more code. So we we decrease the amount of code that we break when we add in other words, if we're adding code, we don't have to test the old code, right? Because we didn't change it, right? It's only when you modify code that you might have broken it, right? But over here, when we add behaviors, we're not modifying and we're not changing existing code, right? We're just adding more code, right? So, so that's object-oriented number six is that you should always be open for extension, meaning you should have a code that allows for adding more stuff, but is designed so that it's closed for modification that we don't need to modify when we add new. No, it's made to be always be added to, but not to be changed, right? So so for example, like I did this actually Tuesday, I did a much better example of a really uh, code. Yeah, like over here, if you notice, I'll just go here real quick. So over here, I had um, where was it? It was called draw shape, right? So over here, for example, this code over here, look at this draw. If you look at this code, what does it do? If you draw a circle, right, then you execute this code. If you're drawing a square, right, execute this code, right? But what happens if I want to add a new type to draw? Then I have to change this code, right? So every time I have a different shape, I'm going to have to modify this draw shape object, right? Right. So in general, whenever you see if statements, them and that generally is a clue, especially if you see a lot of them, then it's a real big clue that there's something that this code could be is going to have to be modified and then potentially broken in the future. Right. So it's better. So, but the code we just did, there's no if statements, right? It's basically, it doesn't say, well, if it's this type of, flying, if it says to fly this way, then we're going to fly, regular. If it says fly this way, then do this, right? There's no if statements, right? We just pass in the type of behavior that we want. So we're not modifying every time there's something different. We don't have to modify the code. Okay, so that's the principle of open for extension, closed for modification. Okay, so in other words, um, it's always safer to just add code to existing code rather than constantly changing existing code. Okay, it makes sense, right? Right. It's always better to modify something to add rather than keep on changing because whenever you change code, that's when you get bugs, right? Okay. Um, okay, so then we went through UML last time. Um, uh, let's see if we get over here. And we spoke about abstract type, right? Right. Abstract we said is what? How do you know something is abstract? If you what? What's the test? What's the easy way to tell? Well, if you could do a new operator on it, right? Then it's what? Then it's not it's concrete. If you can't do a new operator, then it's abstract, right? So an interface, you can't create a new interface using that type. You can't create a new one, so that would be abstract. Um, then inheritance, we said that the problem with inheritance is that you're getting everything, right, from the parent, right? Remember I think we said this, yes, on Tuesday. We said that it has is a relationship. So it's like very strong relationship, meaning that it's like, in a way, it's too strong, right? Because you're getting everything, even things you don't want, right? Let's say I want one thing, but if you're using inheritance, you have to get everything, right? But for example, let's say I like the way something quacks, I'm going to have to get the way it flies also, or the way it displays. So I can't just get part of something, right? I get everything, even right? So that's the problem with inheritance. Inheritance gives you way too much, right? Um, and that because it has that is a relationship, that tightly bound relationship because a child is the parent, right? In object-oriented programming, right? But it's not like humans where the child is not, you can't say the child is their father or is their mother, right? They get something from both, right? Um, but in object-oriented programming, a child is a parent, right? So whatever the parent is, the child is plus. Okay. Um, okay, and then we spoke about the problems. Um, then we said that so the idea is to have loosely coupled code, right? Which is what we did actually. We ended up saying that we use interfaces, right? So in that way, well, actually, we use two ways. So listen, let me just read what I wrote here. It's bad because we force children to act a specific way. Children may act differently. Okay, where's it? Um, what's it? B extends A. B is A plus B's code. A and B tightly coupled. Let me just fix this up. Is that meaning a I want to reuse code or a method, let's say, from a parent using inheritance, I will get everything a parent has. Okay? Okay, so not just what I needed. Okay, so I'll get everything. Okay, that's the problem with inheritance. I get too much stuff. Okay, um, and then um, also um, not for example, but also changing the name makes them change. All children will not may and a will accidentally will change all the children of A. As we said, it's called fragile base class, right? Sounds like a disease, but it means that if you change the parent, it will change all the children. Rate times made to A. Also changing, okay, I'll just leave this out. Okay. Okay. So we said loosely coupled code. Another way would be composition. Um, so basically is what we said. So what the alternative tightly coupled code is, we said to um, okay. So um, what is the alternative tightly coupled? So we said basically number one, is going to be passing in the behavior passing in behavior that to an object, right? So that makes it more less coupled, right? Because we're not inheriting it. We're not inheriting the behavior. We're passing in the behavior to an object. Do you understand what it means by behavior? No, it's an object behavior as an object. So I don't know any better way to say it. So we're passing in behavior to an object. And number two, B is we said we also want to be have the behavior in terms of what it does rather than what it is, right? So the behavior should be um, passed as an interface, right? Because remember, an interface doesn't tell you what you are, it just discusses what you could do, right? So that's the best way. That's the most easy, that's the most generic way to pass in a behavior to another object is by saying, I'm giving you an object that does this. You need this, you need to fly. I'm going to pass you in an object that knows how to fly, right? So I'm going to just that's how I'm defining myself. I'm an object who gives you what you need. Like I'm a cook who knows how to make breakfast. I'm not telling you anything else about myself. I'm not saying that I'm tall, I'm short. I'm not saying that I speak English, that I speak German, French, whatever. All I'm telling you is I can make breakfast. Here I'm telling you, so that is the most general way that we could pass in as many different objects as possible, right? Because we're passing in any object which knows how to make breakfast. Over here, any object that knows how to fly or how to quack. They're all eligible to be passed in to our duck, right? Our duck could use anything that knows how to fly or anything knows how to quack. We could pass it in. We don't have to change the code, right? And that is the best way to do it. So behavior should be passed in the interface to be as general as possible. Okay? So that is this is a strategy pattern. Okay? And we'll do another example on next week. But okay, and then we'll also go over 1, 2, 3, and 4. I don't know when to get messed up. But we'll do it on so far we did 5 and 6, and I'll just get rid of this. Okay. Okay, so we'll pick up on next week, okay? Okay, see you next week. So somebody do a presentation. Okay. Okay, well, the first person always gets the best, it gets extra points. Okay? Because they're the bravest. Okay? Okay, so have a good weekend. Okay.